Within the Milky Way galaxy lies an ordinary middle-aged star surrounded by 9 planets and a handful of space debris. Nearest this star circle the rocky terrestrial worlds. Next is an orbiting belt of boulders and minor planets we call the asteroids. Further out, the mammoth Jovian planets. Further still, icy planetesimals travel toward the sun, producing the wonder of comets. The spectacular worlds that make up our solar system are the nearest objects in the heavens. Yet we are just beginning to understand how they formed and evolved into the worlds we see today.
We can approach the question of how the solar system formed in 2 ways. You can either take the solar system you have now and back up the movie and see what it must have been like to start with, or watch situations now where stars are forming and see if you can deduce that solar systems or planets are forming around those stars at the same time.
We believe that stars form initially from a cloud of dust and gas, and these clouds, we know from measurement, rotate very slowly. As the cloud collapses to begin to form a star, it will begin to rotate faster and faster. And in fact, this cloud will begin to rotate so rapidly that it will form a disk at the equator of the star, where it's rotating most rapidly.
The effects of that rotation will be magnified as the system collapses to smaller dimensions, much as an ice skater, as she pulls in her arms, will begin to spin faster and faster. So will a collapsing molecular cloud begin to spin faster and faster from the conservation of angular momentum. Eventually, the peripheries of the collapsing region will contain too much rotational motion to fall directly toward the center, and instead will fall into a swirling disk around the center where a star is formed.
If you could actually go down in the cloud and see what was there, what you'd probably see is an initial star just kind of building up material, a round object at the center, and around it would be a sort of fat disk of material, of cloud material spiraling into the star. So you'd see a round lump at the center, and then you'd see a disk around that which would grow with time.
Essentially what you have is not material continually raining down in a sphere. The inner material flattens out into a pancake-like structure around the star. Of course, you will have a spherical envelope where material is still raining down onto the disk and the star at this early stage. But from this disk, material is constantly moving in, accreting onto the star.
You get material settling in at all distances from the star into the equatorial plane, and so it looks like a disk, basically like a record spinning. And as more stuff comes in, it has more spin and it lands further out, and the disk just grows bigger and bigger. Somehow the disk has to get rid of this spin in order to give the material down to the star. And the process of giving it down is called accretion, and so we call a disk, which is somehow getting rid of spin on its outside and letting material come through it, we call that an accretion disk.
As the evolution of this envelope or core, disk, star object proceeds, what happens is that the seed at the center gradually increases mass, both from material infalling directly onto the star and accreting through the circumstellar disk.
An accretion disk works just like our solar system. Very near to the star, it has to go very fast in order to stay up in orbit around from the star, and if it's further away, it goes more slowly. So that if you can see spectral lines which come from different parts of the disk, you would expect to see evidence of rapid motions near the star and slow motions further away from the star.
At the center of the region, you have a protostar, a young star forming, and then orbiting around the young star is additional dust and gas. And the dust grains are really tiny, they're microscopic, but The importance of these dust particles is we think that when they are in orbit around a young star, they start to clump together, partially due to gravity and partially due to just chemical stickiness.
The dust particles that obscures light can grow by sticking together into larger and larger bodies, much as the dust under your bed will get together and form larger and larger dust bunnies. So one can imagine that these dust grains will aggregate in the solar nebula, in the disk of the gas and dust that surrounds the new sun.
If there's a dense enough layer of these dust grains, then they'll bump and stick together and make bigger things. And that if their motion is gentle enough, they'll start to attract each other gravitationally. This is called gravitational instability, which usually means that other things are quieted down enough that gravitation is the only significant effect left.
This material, this dust in the disk, over time will collide with other particles in the disk, and some of that will stick together to form larger and larger particles over time. As these particles grow, they get to be called planetesimals. They're not quite planets, but they're the parts that may stick together later to form planets.
It turns out in the solar nebula, material is orbiting around very quickly, but material close together is orbiting basically with almost the same kinds of velocities. So the velocities aren't all that great when they come together. Also, the material is rather warm and perhaps molten at some parts of it, so you get material accumulating into larger and larger planetesimals. Also entrained in this material is gas, and the gas tends to slow things down and cause friction, which also helps in these collisional processes and these accumulation processes. We think that at some point when a star really turns on in terms of nuclear burning, that a solar wind is generated. We do see that in certain stars, like the T Tauri stars. They have very, very strong solar winds, which tend to, by radiation pressure, get the gas away from the planets and away from the center of the disk. They tend to clear the disk. And this may be one mechanism for clearing away the gas after the planets form. In other words, a mechanism which tends to turn off this process of planetary formation and clear the disk.
Each night, astronomers at major observatories focus their telescopes on distant stars in search of evidence to better define the solar nebula theory.
Well, we're all trying to explore the cosmos, I guess, so we're all adding one more piece to the puzzle, or trying to. There are two projects that I'm working on up here. They're both small parts of a much larger puzzle having to do with where do stars like the sun come from, how do they form, and how do they form planets. The ultimate goal, I suppose, is to talk about how planets form and where and when they form, but we're not quite there yet. Planets are hard to find. They are not very bright, and they're not very big, and they're very close to these bright, big objects called stars, so it's hard to see them. Our best chance is probably to find them as they're being made. We can see dust. We can take an object the size of the Earth, pulverize into dust, spread it out through the solar system, and you can detect that from far away because dust will have a large surface area. It's a large radiating body. I take spectra of the object that's there and find out what it is. And we're working mainly in the belt of Orion, looking for young stars there. The belt of Orion is a region that's been forming stars for about 10 million years. The three bright stars in the belt are 10 million years old. They're very massive stars. They're not anything like the sun. We're in this search for protoplanetary disks, dust out of which planets can form, and we want to know how fast do planets form. Are planets forming 5 to 10 million years after the star? Is there still dust surrounding the star 5 to 10 million years later? My feeling is that no, planets form very quickly. Now we know the ages of the stars we're looking at, so we can say that you must have formed planetesimals and started the planetary formation process by a certain time in the lifetime of a star.
To examine the question of planet formation in a different light, astronomers focus arrays of radio telescopes on the disks around newborn stars.
The disks that we see surround stars that are about the same mass as the Sun and have the age that the Sun had when it would still have had a nebula around it. Probably planets have not formed in these disks. However, there is evidence that the material that we observe around these very young stars, apparently in disks, is a little larger in size. The particle size is larger than you might normally expect in the interstellar medium, and as a result, we suspect that already the initial stages of coagulation that precede planetary formation may be occurring. Another of the reasons that we think that these disks may in fact be protoplanetary is that they show quite strong evidence, and the evidence seems to be becoming stronger as time goes on, for rotation, and not just rotating like a solid body. To our great surprise, when we first looked at what has become something of a prototypical protoplanetary disk, H.L. Tauri, Steve Beckwith and I discovered that the gas actually rotated in Keplerian orbits. That is to say, it rotated possibly in ellipses, but most importantly, the gas closest to the star rotated faster than the gas far away from the star, just the way that we find Mercury rotates much faster around the Sun than, say, Pluto does.
We're picking up the source.
While radio astronomers detect the hot dust around newborn stars, other astronomers use infrared telescopes to observe the cooler disks around slightly older stars.
The objects called dust disks were discovered by the IRAS satellite in 1983. They are small grains, meaning smaller than dust grains, and the clouds of them are transparent, and they are orbiting many of the nearby stars that are in the same developmental stage as our Sun. In other words, completely finished. The star is completely finished forming, and the star is poking along in its so-called adult life, main sequence life.
One of the problems, of course, for looking at these disks is that if you have an older disk, your star is much brighter and relative to the surrounding material is likely to obscure it, particularly at optical and infrared wavelengths where you're going to see scattered light from the star. Smith and Terrell, in their images of Beta Pictoris, have managed to overcome this by using a coronagraph in which they essentially block out the light from the star and therefore can see the scattered light around it.
The Beta Pictoris disk is actually several tens of times larger than the planets in our solar system. The interesting thing about Beta Pictoris is that it now appears that the center of the disk is hollowed out. And that void space is about the same size as our solar system. The void space is actually very important because we now believe that planets may be orbiting and existing inside that area, close to the star. So if you can imagine our planets orbiting very, very close to a star, surrounded by a disk of material maybe 20 times larger than our solar system. That's what we're seeing.
The dust disks found around nearby stars by the infrared astronomy satellite are probably a missing link between the stage that we pretty well understand, which is called the T Tauri stage, when a star that's not quite finished forming has around it a completely opaque and thick disk of material that's probably going to turn into the planets, and later on our own solar system where there's no gas and it's fairly empty and the planets have finished forming.
There are a handful of stars that have been seen nearby that contain disks of material as seen in the infrared. When we go out further to star-forming regions like Orion, where there are hundreds of stars, there are tens and maybe even hundreds of stars which also contain disks. So we're starting to see these things as a very, very common factor and a very common phenomenon in star formation.
So from observations, we now can show that almost every star, when it forms not only the stellar core, but that there's a disk of material around it that's also rotating. And this material is exactly the right mass, it's got the right dimensions to form a planetary system.
Observation of dust disks gives us insight into how a planetary system might form. Yet, our solar system is the only example that we've been able to observe directly.
The way in which we believe the solar system formed was out of a cloud of interstellar gas, which eventually collapsed in upon itself. And in doing so, any kind of rotational motion in the cloud tends to form a disk of rotating material. In fact, the fact that the planets themselves in our solar system are a fossil remnant of that pre-solar nebula.
If we look at clouds in the interstellar medium, we see stars forming at the centers of those clouds, and we see a small amount of mass around those stars, perhaps just a few % of the mass of the star. And indeed, when we look at our own solar system, we see just a few % of the mass of the sun is needed to explain all of the material that condensed out.
One sees that there seem to be 2 or 3 different types of planets. There are the rocky terrestrial kind of planets, the Earth and Venus and Mars, for example, Mercury, made out of mostly silicate kind of rock, kind of stuff we're all familiar with. Then there are the gas giants such as Jupiter and Saturn, Uranus and Neptune, and then there are a few objects such as Pluto, which are probably mainly ice-covered worlds.
There's not very many large objects in the solar system today. There's a relatively small number of planets. Now, this situation must have been different in the past. As the gas dust nebula cooled, small objects condensed out, then these small objects collided to make medium-sized objects, then eventually they collided to make bigger objects.
As a terrestrial planet grows, it develops higher and higher gravitational attraction. The faster things fall into the planet, the more energy they deposit, the bigger the splash, if you will, and the more heating. And it is, in models of planet formation, it's calculated they got hot enough to melt iron and so forth when they were smaller than Mars is now.
All planets went through heating. Some of the heat may have come from radioactive minerals that were trapped down inside the planets, gave off heat, gradually warmed up the interior. They got so hot inside that they melted, and what happens when you melt rock, the metallic compounds and elements they're heavier, they're denser, they sink to the center. And so you formed a metal core down inside. The lightest minerals float out to the surface and make a crust of rocky material. That's what happened inside planets. That's what happened inside the Earth. We have an iron core. We have a crust of silicate rock, 5 kilometers thick, a little thicker under the continents. We have this big mantle between the core and the crust.
From the density alone, we know that both Venus and Mars have to have dense iron cores, and in that respect, they're similar to the interior of the Earth. In other words, the density of Venus and the density of Mars is much greater than the density of ordinary silicate rocks. So we have something very dense in the interior, and this probably is an iron core.
So an intense heat and gravity forged the planets in layers. But as they cooled, the rocky remains of the solar nebula continued to rain down upon them.
Early on in the history of our solar system, there was a great deal of violent bombardment. We believe that when the solar system first formed, janitorial services were not up to snuff. And there was a lot of debris left over that were just flying around hitting things.
It was the debris left over from planet formation. The planets themselves formed out of all this junk, this dust particles which had grown into golf ball sized things, which had grown into basketballs, which had grown into floating mountains the size of asteroids, a mile across and 50 miles across, 100 miles across. It accumulated into these big bodies, and then they began to run into each other and make craters on each other.
Here on Earth, a lot of the evidence for that early bombardment has been erased by catastrophic processes. Mountain building, volcanoes, weather, oceans, teenage children, all kinds of destructive processes have completely destroyed any history of that violent past. But on worlds where there is no air, where there is no weather, we still have remaining many of the fossilized records of this ancient period of violent collisions.
While cratering battered the surface of the planets, the factor that perhaps most affected their size was their distance from the sun.
In the inner solar system, we have small rocky bodies, or terrestrial planets, and in the outer solar system, we have the giant planets. Jupiter, Saturn, Uranus, and Neptune. And the reason that these giant planets are so large compared to the inner planets is that they contain ice in addition to rock.
When you think about the solar nebula, remember that its chemical composition was probably basically the same everywhere. There was water vapor in the inner solar nebula, and there was water vapor in the outer solar nebula. The important difference is the temperature.
Close into the sun, you had high temperatures, which meant that only rocks could be solid, and therefore the planets were made out of those solid materials. As you go out further into the cold outer parts of the area around the sun, the temperatures dropped low enough that ice could form, water ice and other kinds of ices. And in addition, the bodies were big enough that they could attract and keep gas, mainly because of the very low temperatures.
When the solar nebula surrounded the forming sun and the planetesimals began to condense from the solar nebula, any material that was closer than a magic line that we'll call the ice line, any material closer than that ice line could only condense if it was rock or metal. Material beyond the ice line could condense even if it was water vapor. And so beyond that magic line, there was a tremendous amount of water vapor condensing to form ice crystals.
Those ices constitute the vast bulk of condensable solids in any cosmic gas. Because they can exist in solid form beyond Jupiter's radius, the cores that formed out there, the planetary cores, grew to much larger sizes than they did in the inner solar system because they had access to much larger reservoir of raw material.
Relatively hot planets like Venus and the Earth have a tough time holding hot molecules at their surfaces in the form of atmospheres. Now, we can hold oxygen and nitrogen and carbon dioxide because they're relatively heavy, but gases like helium and hydrogen are moving too quickly to be held by the Earth's gravity, so they can escape very easily. But when you go out into the outer parts of the solar system where Jupiter and Saturn are, then the temperatures of the hydrogen and helium are low enough, the molecules are moving more slowly, they have trouble escaping from the gravity fields of Jupiter and Saturn, and they can retain most of even these very light gases.
And so the planets that grew in the outer part of the solar nebula, beyond the ice line, grew rapidly and became very massive. It's logical to think that the planet that grew just beyond the ice line, where the nebula was still at its densest and where the ice could condense, would become the most massive. So Jupiter is the most massive planet because it is the nearest of the Jovian planets. It's the one that formed just beyond the ice line. And that takes us to the next step, to believe that in most solar systems, all through the universe, there has to be a Jupiter just beyond the ice line.
As the solar system further developed, the tremendous gravitational pull of Jupiter influenced creation of the asteroid belt and affected the paths of meteors and comets. Enormous gravity also enabled the giant planets to form ring systems and hold a large number of satellites.
Jupiter has a system of at least 16 moons that we know about, and probably a good number that we don't know about that are too small to have been detected. And as we move out into the solar system through Saturn, Uranus, Neptune, and even Pluto, we find that each of these planets has at least one moon, and in some cases, for example Saturn, at least 17 moons. We think that the moons, in most instances, represent material left over after the formation of the individual planet, and that it represents material that has undergone a certain amount of chemical and physical processing over the lifetime of the solar system. As we continue to study the planetary bodies and the other small bodies in the solar system, we learn more about their compositions, we learn more about their origins, and we can begin to understand more about the formation of the solar system and its chemical and mechanical evolution in the nearly 5 billion years since these objects were assembled from the gas and dust that constituted the original solar nebula. We're especially interested in the connection of our solar system to other planetary systems surrounding other stars.
In terms of how the planets around other stars might be arranged, we expect it to be very similar to our own situation for several different reasons. One is that you can't have a planet too close to the star because the solid material just wouldn't be able to condense if it was too hot. And if you go to the outer part of the solar system, there's too little material and it takes too long to bump into its mates to pile up into bigger piles to make a planet. And so the outer limit is basically defined by how long it takes to make a planet, how long the stuff would take to accumulate and pile up into a planet. And so that's why we think that Neptune is the last planet and there's not a 10th and an 11th and a 12th. Notice that I don't think that Pluto is a planet. I think that Pluto is the biggest piece of debris left over from the planet's forming. But we expect that there should be about 10 planets, 5, 10, 15 planets, because that would be how the material would sort itself out in a situation, a disk around a star.
The solar nebula theory tells us that the planets around the sun, including the Earth, formed as a byproduct of the formation of the sun, as a byproduct of star formation. If that's true, then most stars should have planets around them. All single stars, perhaps, should have planets around them. Further, if you think about the rules that govern the formation of planets, we think that rocky planets should form close to the star, and massive, low-density giant planets should form further away. Most solar systems should look like our solar system, with terrestrial planets near the star and Jovian planets far away from the star. So, planetary systems should be very similar to ours, and if we're right, there should be billions of them.